So if you follow environmental news, you are likely familiar with, well, one of the most accepted and frankly terrifying narratives of our time.
Yeah, the consensus that humanity is currently driving the planet into its sixth great mass extinction.
Exactly. We're talking about a biological catastrophe,
Yeah.
on par with the meteor impact that wiped out the dinosaurs 65 million years ago,
Yeah.
potentially losing 75% of all species.
It's a huge claim, and it's everywhere.
It really is. It shapes international conservation policy, it directs billions in funding, and, well, it raises alarm globally, doesn't it?
Absolutely.
But here's the critical question we want to dig into today. Is this dire prediction fully supported by the actual verifiable data?
Hmm.
Today, we are taking a deep dive into a really crucial and I'd say provocative paper that challenges this whole premise directly. It's called Emergence of a Sixth Mass Extinction by
Oh.
John C. Briggs, published back in 2017 in the Biological Journal of the Linnean Society. Our mission here is to investigate whether the foundational evidence, the stuff often presented in prestigious journals, actually supports this extreme catastrophic prediction. We're trying to get past the headlines and look at the hard numbers.
And this critique isn't just some academic squabble, right? It's vital because this idea, this prediction of a looming catastrophe, has profoundly influenced global conservation strategy for decades now.
Yeah, decades.
Think back to the 70s, the 90s. You had influential figures like Myers, Wilson, Leakey, and Lewin. They were estimating species losses in the thousands, maybe even tens of thousands per year, mostly due to human activity.
Huge numbers.
Massive. So Briggs is essentially asking us to, pause and check the receipts. His core thesis is pretty sharp. Unless we have concrete evidence of substantial net species loss.
Okay, what does net mean here exactly?
It means losses that dramatically exceed the natural background rate and also account for any concurrent gains through new species arising.
Got it. So losses minus gains.
Exactly. And Briggs says without that evidence, the claim of an emerging mass extinction is, and this is his phrase, speculation without substance. He's really forcing us to redefine what we're actually measuring.
Okay, let's unpack this. You mentioned the background rate. Briggs starts by pointing out that previous estimates, those really high ones, were often hugely exaggerated, sometimes maybe even deliberately to capture public attention and funding.
That's part of his critique, yes. But the key methodological flaw he identifies is, I think, even more fundamental.
Which is?
The historical failure to consider biodiversity gain or speciation alongside biodiversity loss, extinction. It's like trying to figure out your financial status by only looking at your expenses without ever checking your income.
Right, you'd get a skewed picture pretty fast.
Exactly. So before we can even start to determine the human impact, we have to establish a relevant baseline, a normal expected rate of extinction.
Okay, so how do you do that? What's normal?
Well, Briggs argues we should look to the Pleistocene epoch as the most appropriate baseline.
Why the Pleistocene?
Because it represents the best-known fossil fauna, geologically speaking, and it's the most recent analog to the present day, right before major human-driven changes really kicked in. It gives us a window into natural processes.
Makes sense. And what kind of rate does he establish from that Pleistocene data?
Based on earlier work, particularly by McLeod, Briggs establishes a low long-term historical background rate. It works out to approximately 0.5 species per year. Half a species.
Half species per year, naturally. Okay, so over the 500 years we typically analyze in these studies, say, since the year 1500, that means we'd expect about 250 species to have gone extinct naturally just due to planetary turnover, nothing to do with us.
Precisely. Now, with that baseline, we can start to properly quantify the human-caused loss, at least in the groups we know best, like terrestrial vertebrates, mammals, birds, reptiles, amphibians.
The ones we track well.
Right. According to the IUCN Red List, which is the gold standard for this, 338 terrestrial vertebrate species are documented as having become extinct since 1500.
Okay, 338. That still sounds like quite a few.
It does, initially. But here's the crucial step Briggs takes. If we subtract that expected background loss, those 250 species, from the 338 documented losses.
The net loss calculation.
Exactly. The net loss directly attributable to human causes in this most monitored group over 500 years comes out to only 88 species.
Wait, 88? Over 5 centuries.
88?
It flies directly against everything we've been hearing since the 90s, right? How could those early estimates claiming thousands lost per year have been so catastrophically wrong?
Well, according to Briggs, they were largely wrong because they extrapolated potential losses based on habitat reduction models rather than counting actual documented species extinctions.
So theoretical versus observed.
In essence, yes. Briggs's analysis of the verified data translates this 88 species loss into an approximate human-caused extinction rate of only 0.18 species per year for terrestrial vertebrates.
0.18.
It's a rate that is thousands of times lower than those really sensational estimates that drove the original alarm.
That is quite profound. And Briggs doesn't stop there, does he? He brings this into an overall calculation, trying to include less documented groups like insects and marine species.
He does. He attempts to estimate across the board, acknowledging the data gaps, and arrives at an approximate total human-caused loss of maybe 759 extinctions over that entire 500-year period.
Okay, 759 total. If you put that into a simple annual rate,
You get roughly 1.5 species per year.
1.5 species
Yeah.
annually,
Yeah.
verifiably lost due to human activity.
That's the figure Briggs presents based on the documented evidence up to 2017.
That single figure just fundamentally changes the perspective on the crisis, doesn't it? It suggests the global biodiversity count hasn't yet hit that catastrophic 75% mass extinction threshold. Not even close, based on these numbers.
The difference in scale is, well, it's impossible to ignore.
Wow.
But this leads us to the next critical question, right? If the number is so much lower than predicted, where are we seeing the verified damage? Because extinctions have happened.
Yeah, location matters. Most people probably visualize species disappearing from, I don't know, the Amazon rainforest or the African savanna.
Right, the big continental areas.
But the data tells a really different story. Research analyzed by Briggs, particularly work by Lowell and Eschenbach from 2012, found something striking.
What was that?
That more than 95% of recorded bird and mammal extinctions over the past 5 centuries took place specifically on small, isolated oceanic islands.
95%. Wow.
The numbers are stark. Only 3 out of 61 documented mammal extinctions and just 6 out of 128 bird extinctions actually happened on the continents. The overwhelming majority were island species.
And the implication there, according to Briggs, is that the loss of these isolated, often endemic island species, well, definitely regrettable.
Of course.
It has had little or perhaps no demonstrable effect on the ecology and evolution of the major continental systems. He frames it more as a series of localized catastrophes, often caused by invasive species introduced by humans, rather than a sign of an imminent global collapse of those large continental ecosystems.
Okay, but isn't classifying island extinction as just localized a bit? I don't know, potentially dismissive? I mean, those are unique, irreplaceable evolutionary lines, even if they weren't part of, say, the Amazon ecosystem.
It's definitely a point that sparks debate. And Briggs isn't dismissing the tragedy of losing any species. His argument is more about differentiating between geographically contained losses, however sad, and evidence for a massive system-wide continental ecosystem crash, which is what a mass extinction usually implies.
You're saying the evidence for that specific kind of crash isn't there yet in the numbers.
Exactly. And to truly measure if a mass extinction is underway, he argues, we absolutely have to look at the biggest group by far. The insects.
Right. The vertebrates we focus on, mammals, birds, there are only about 25,000 species total.
Peanuts, relatively speaking. Insects make up an estimated 90% of all terrestrial animal species, possibly 5.5 million species or even more. If a mass extinction event is truly happening on land, it should be devastatingly obvious in the insect world.
Okay, but how on earth do you measure extinction in a group that enormous and often poorly studied?
You can't track them all. So Briggs looked at studies using well-known, relatively well-monitored insect groups as surrogates or indicators for the overall rate. Things like butterflies, tiger beetles, dragonflies, damselflies groups people actually notice and record.
Sensible approach. And what did that reveal?
Well, this is maybe one of the most shocking parts of the analysis. Out of about 25,260 evaluated species within these highly visible, well-documented insect groups, researchers found evidence for only 3 species having become extinct over the past 500 years.
3 out of over 25,000 studied.
3.
So you really have to ask, like Briggs does, if the real extinction rate was truly thousands of times higher than the background rate, as some early models suggested, where are the millions upon millions of dead insect species? We should be tripping over them, metaphorically speaking.
It's a huge discrepancy, and that finding is critical because it circles us back to the other side of the ledger, the income side, the biodiversity game.
Sushi.
Right.
Briggs cites substantial evidence suggesting that speciation, the formation of new species, hasn't stopped. In fact, it may have actually matched or even surpassed the documented losses over the past 500 years, partly driven, ironically, by human activity like introductions.
How so?
Well, think about it. Terrestrial species diversity has actually increased on many oceanic islands and even in some continental regions because humans brought in new species intentionally for agriculture or accidentally.
Right. Non-native species adding to the local count, even if they cause other problems.
Correct. And perhaps more powerfully, Briggs points to a large-scale study by Dornalis and colleagues published in 2014. They looked at time series data for over 35,000 species across 4 decades.
And
They found no negative global trend in species richness. The total number of species globally appeared to be stable or possibly even slightly increasing during that period. Stable or increasing. Okay, so if the data doesn't strongly support an ongoing mass extinction on land, based on Briggs's analysis, what about the oceans? They cover 70% of the planet. That's often presented as the next big crisis area.
he addresses that too. He looks at the second major fear of the marine crisis by analyzing another significant paper, Payne et al., from 2016. That paper suggested an emerging oceanic extinction based on comparing threat levels in modern versus fossil records.
And Briggs's take.
His analysis of the documented marine losses is just as forceful as his terrestrial one. He points out that only about 18 marine species have been verifiably lost in the last 12,000 years, and crucially, none have been documented as extinct within the last 30 years.
0 in the last 30 years.
According to the documented records he reviewed. So he concludes the danger of an emerging mass extinction in the ocean is, again, equally unsupported by the current verifiable data on actual species loss.
But did that Payne et al. Paper offer anything useful then?
Oh, absolutely. And Briggs highlights this. Payne et al. Did make a really important ecological finding, and this is where the data gets crucial, regardless of the species count debate.
Okay, what was it?
They found that the threat of extinction among living marine genera is strongly associated with body size.
Body size. Meaning bigger things are more threatened.
Precisely. What this indicates is that human influence, largely through intensive fishing and harvesting, is highly selective. We're preferentially removing the largest individuals from marine populations.
Okay, I can see how that would happen. We target the big fish.
We do. And that size selectivity has potentially devastating consequences, even if the total number of species doesn't plummet immediately.
How so?
Well, we're selecting against the largest, oldest females in many fish populations, and research has shown again and again that the larvae produced by these bigger, older females often have exponentially higher survival rates compared to larvae from smaller, younger fish. They're disproportionately important for recruitment.
So taking out the big moms has an outsized effect on the next generation.
A massive effect. When you remove the biggest, most productive individuals, you can cause an exponential reduction in the number of successful offspring. You can shorten the overall reproductive season for the population, and ultimately, you drive a decline in the average and maximum body size of fish throughout the ecosystem.
And that matters because
Because the key takeaway here that Briggs emphasizes is that this kind of size-selective pressure impacts ecosystems potentially more profoundly and definitely more rapidly than just a slow decline in the number of species. It changes the whole structure and function.
that makes sense. It's not just about names on a list, it's about the ecological roles those organisms play, and size is often key to that role.
Exactly. And this profound ecological impact of size-selective pressure serves as the springboard for Briggs's main takeaway message for conservation.
Which is?
If the crisis isn't currently best defined by mass species extinction, then we need to fundamentally shift our focus. The greatest conservation problem we face right now, he argues, is not species loss per se, but massive population decline, the sheer reduction in abundance.
Okay, this seems like the verifiable crisis that should be front and center. We might not be losing 75% of species globally yet, but we are absolutely decimating the number of individuals within many species.
That's where the data is alarming. Let's look at the Living Planet Index, for example, which tracks population sizes over time. Between 1970 and 2010, just 40 years, terrestrial vertebrate populations declined, on average, by a staggering 52%.
Half gone in 40 years.
Half the individuals gone. But it was even worse in freshwaters. Freshwater populations suffered a shocking 76% loss in abundance during that same period.
76%. That's almost incomprehensible. 3 out of every 4 individual animals in those systems gone in less than a human lifetime.
It's catastrophic. And in the marine environment, overall populations declined 49%, but for some key groups like large pelagic fishes, tunas, billfishes, populations plummeted by 74%. That 76% figure for freshwater, that feels like the real emergency happening right now.
Yeah.
And critically, these drastically reduced populations mean severely reduced genetic diversity. This massive decline is what creates an extinction debt. It's like a huge future liability accumulating on nature's balance sheet.
Extinction debt. Explain that a bit more.
Well, small remnant populations, they suffer from inbreeding, which reduces their health and adaptability. And crucially, they can suffer from something called the alley effect.
The alley effect.
Yeah.
Right? That's where small group size itself becomes a problem for survival.
Exactly. It's a phenomenon where population growth rate actually declines at low densities. For example, if you have too few individuals, they might not be able to find mates easily, or they can't effectively defend territory together, or maybe they can't hunt cooperatively if they're social predators. The small size itself hinders survival and reproduction.
So these critically small populations, even if they're still hanging on, are incredibly vulnerable.
Extremely vulnerable to any future environmental changes, a new disease, habitat loss, and perhaps most importantly now, climate shifts. They are essentially pre-doomed, living on borrowed time, unless there's active intervention.
Okay, so let's bring this together. Briggs argues strongly that the documented extinctions are much lower than the scary headline suggested, and that global biodiversity richness, the species count, might even be stable or rising due to speciation and introductions.
Right, that's his analysis of the species-level data.
But the looming future threat, the real ticking time bomb caused by these massive population collapses and the resulting extinction debt, is undeniable. That's the crisis we can clearly see in the numbers.
Precisely. And this realization, he argues, should force a significant change in conservation priorities and how we measure success.
So if the mass extinction claims were perhaps exaggerated based on the data up to 2017, what does Briggs suggest we focus on now? What are the next steps for research?
He suggests two key paths forward. First, we absolutely must continue, and probably expand, long-term monitoring of those well-known insect groups, the butterflies, tiger beetles, dragonflies. Use them as reliable indicators, as surrogates for the overall terrestrial extinction rate. If a mass extinction does start accelerating, we'll likely see it there first.
Keep eyes on the canaries in the coal mine, so to speak.
Kind of, yeah. Second, he points out that the current low recorded extinction rate in the C0 documented in 30 years seems suspiciously low, maybe reflecting poor monitoring rather than reality. So there's an urgent need for much better long-term monitoring of familiar marine groups, especially fishes and corals, to get a true picture.
Okay, monitor insects better, monitor marine life better. Now here's where it gets really interesting, connecting this to the even bigger picture. If biodiversity richness might be holding steady or rising for now, what's the single most immediate, large-scale threat that could derail that potential continuation of biodiversity?
Yeah, the elephant in the room. It's clearly the ongoing global temperature increase due to atmospheric pollution, climate change.
Right.
Climate change is projected to cause the extinction of numerous species simply by destabilizing the environments they're adapted to, making habitats unsuitable faster than many species can adapt or move. And it will hit those already small, high-risk populations, the ones carrying that extinction debt the hardest.
So climate change basically magnifies the alley effect and calls in that extinction debt much faster.
That's a good way to put it. It's the great accelerator for future extinctions, acting on populations weakened by past declines.
So what does this all mean for you, the listener, trying to understand the state of the planet? The main conclusion from digging into Briggs's work is that the evidence for an already emerging mass extinction, defined in that catastrophic sense of 75% species loss, seemed, at least in 2017, based more on speculation and exaggerated estimates that didn't fully account for species gain.
Right. The verifiable crisis, the one the numbers scream about, is the collapse of population abundance. That's what's creating this massive extinction vulnerability for the future.
So maybe we need to shift our collective mindset. Instead of primarily worrying about the very last individual of a species dying, by which point it's often already functionally extinct anyway, maybe we should focus intensely on the first time a species population drops below a critical threshold, like that horrifying 76% decline we saw in freshwater systems.
Focusing on abundance and functional roles, not just the species list.
Exactly. Thinking about conservation primarily through the lens of population recovery, maintaining genetic diversity, and even ecological factors like body size structure, rather than just the species count. That might be the most important strategic shift we need to make globally. It's certainly something to mull over.
It definitely reframes the challenge. Thank you for joining us for this deep dive.